So let me start today's class. Okay. So today we'll be talking about Mos structures. Okay. So I'll talk about Mos transistor theory, and then later we'll just move on to the consecutive topics like CV characteristics and stuffs. Okay. So this is a kind of metal oxide semiconductor structure where when you don't have any potential difference between the gate and the source, still there exists a channel between the source and the drain. Okay, so we call that structure as a depletion type Mosfet. Okay, so as a quick picture, let me take can you just tell me what type of transistor is this? Is it an N type or P type?
NMOS.
Okay.
NMOS.
Okay. So everyone agrees, right? So it's a kind of N type. Okay. So in this case, what I said is that there exists a channel. So even I would have this electrons being created when the potential difference between the gate and the source is basically taken as 0. Okay, so in this case, the VGS was taken as 0, and still there exists a channel between the source and the drain. Okay, and this is an N-type MOSFET, or NMOS is what is shortly called. And the next thing is we just want to talk about the enhancement type. Okay, so in the case of an enhancement type, by default, we will not have this kind of channel between the source and the drain. Okay, so that doesn't exist any channel until otherwise we have some sort of potential difference between the gate and the source, which is greater than the value of VT. Okay, and we call that type of transistor as enhancement type structure. And how this MOSFET is basically different from BJT. I'll just derive this difference right away from this particular term. Okay, so what do we mean by this bipolar?
Charge carrier.
Current flow by both sides, electrons and holes.
Okay, the current through this BJT is basically due to both majority as well as magnetic carriers through the device, right? Because I guess you might be familiar with this active region where the emitter base would be like forward biased and the collector base would be like reverse biased. Okay, so you would have both the type of carriers just trying to move around in order to have the conduction. Whereas in the case of a MOSFET, the story is different. Okay, so in this case, we have only one type of carrier that makes a conduction between the source and the drain, and we generally call this as a unipolar device. Okay, whereas a BJT is known as a bipolar device, just because of the conduction happens because of both majority as well as magnetic carriers. Okay, so which is the most widely used structure between the depletion as well as the enhancement type? Any guesses?
Enhancement type.
Yeah, it is the enhancement type that is most widely used, just because we just want to turn off the device when we have the value of VGS which is less than VT. Okay, even in this particular course, until otherwise we specifically say that we are talking about a MOSFET about depletion type, we always assume that whatever the type of MOSFET that I'm going to discuss from now on, it will be only on of enhancement type. Okay, so this is a kind of MOSFET which doesn't have or less than VT, whatever it is. Okay, so now let us move on to the next one, which is Mos structure behavior. Okay, so I guess you might be familiar with this naming convention of MOS, right? So M stands for metal, O stands for oxide, and S stands for semiconductor. Now, the behavior of this MOS structure has to be studied, and this is something which is more important for us to understand the behavior of the current that flows through this MOSFET. Okay, so we first try to concentrate on this MOS structure, and later we'll just jump on to the CV characteristics, try to understand how does the electrical profile as well as the potential profile varies, and then we just try to see how the capacitance actually changes whenever we vary the potential across the MOS structure. Okay, so in today's class, my major focus would be on this MOS structure, and probably we'll have a glimpse of the entire MOSFET structure, and then we'll just revert back to this MOS structure again when we talk about the CV characteristics. Okay, yeah, so let us try to have this behavior. So let me take a P-type substrate. Okay, so the semiconductor that I'm going to use for the entire discussion, by default, I'm just going to assume that it's always a p-type semiconductor. Okay, and we have this oxide, and then this would be your metal, and this is your p-type semiconductor. Now, let us try to fix some sort of potential difference between the metal and the semiconductor. Okay, and let us vary this potential, or let me rather write it as V, from a negative value to a positive value. Okay, so it is something like this. Okay, so now what happens when I have V that is equal to a negative value? Now we know that the negative polarity would be here and the positive polarity would be at the bottom, and in turn these negative polarity will try to push some of the negative charges onto this metal. Okay, these electrons that comes through this negative terminal of the voltage V would then get settled over here. Okay, so when you have a lot of electrons that is between the metal and the oxide at the interface, what happens? What type of reaction that happens across the p-type material? We already know that the p-type is all, what I have is the majority carriers, which is all filled with holes. Okay, so let us assume that by default, I have an equal concentration of holes across this particular p-type semiconductor. Now, the moment I have a negative potential, what happens on this interface between the oxide and the semiconductor? So let me write this one as O and this one as S. Okay, so between these two interface, what exactly can happen? Any guesses?
So hole concentration will increase near the oxide layer.
Yeah, so we know that the Newton's law, right? So whenever we have the opposite charges, they tend to attract each other. And due to which, what happens is that the concentration of the holes that are near to the interface between the oxide and the semiconductor will be much higher. Okay, we have a lot of holes concentration than compared to the bulk area. We call this entire remaining area as the bulk. So throughout, when I try to compare the concentration of the holes in the bulk, the concentration at the interface will be much higher just because of the electrons that I have across the metal. Okay, so and for time being, I'm not going to get more in depth about the electrons and holes as of now. I just want to talk about the behavior of the structure, and we have a specific name for each of these cases. Okay, now we call this action as accumulation. Okay, this action where you have more number of hole concentration at the interface between the oxide and the semiconductor, we call that action as an accumulation when we try to have a negative charges on the metal oxide interface. Clear? So now let us try to slowly push this voltage V in the positive direction. Okay, now it's a p-type, and right now we are having a voltage V such that the voltage V is between these values. Okay, so I'm having a voltage which is a positive voltage, but still this voltage V is not that much positive, okay, than compared to the value of the threshold voltage. I guess you might be familiar with this threshold voltage definitions. For time being, I'll just assume that you know what is threshold voltage. Okay, I'll talk about this threshold voltage later, but as of now, let us have this a small bit of positive potential across this V. Now, this positive potential will actually translate some of the positive charges on this particular metal, and that positive charges would then get landed on the surface between the metal and the oxide. Okay, now what happens here? Because we know that the p-type, the majority carriers are holes, and again from Newton's law, we know that the like charges will always try to repel each other. Okay, now because I have a positive charge on the other side of the interface, these positive charges that were there near the interface between the oxide and the semiconductor would then be pushed off. Okay, there is a repelling of positive charges away from this oxide semiconductor interface, and due to which, what happens at this particular point? So when you move away the positive charges away from this interface, what does it leaves?
Depletion region.
Yeah, we have a depletion region, but actually it leaves out something known as negative ions. Okay, these negative ions actually generally fills up your depletion region. Your answer is right, but what does it leave behind is nothing but the negatively charged ion.
Sir, how these ions are exactly formed, sir?
Say, for example, you have valence band, and for the silicon, there will be 4 valence electron that would be surrounding the silicon nucleus. And if you kick off one of the electron away from this, then what happens is that it becomes a positive ion. Okay. Similarly, if you have some sort of the other way around is like whenever you try to push some of the electron inside this, then this can become a kind of negative ion. Okay. So you are trying to create, you are trying to disturb the charge neutrality of a particular atom, and due to which it becomes a kind of ion. Did you get it?
Sir, but in this case, near the depletion region, how the charge is liberated or accepted?
Okay, so basically, in order to create a p-type semiconductor, we need to have some sort of dopants. Okay, so the dopant that I needed generally is a kind of trivalent. So what does it mean by a trivalent? Is nothing but the electrons around the valence band would be just 3. Okay, but for a silicon atom, it requires 4 valence electron to completely form a covalent bond with the neighbor. Okay, so this leaves out some sort of holes. Okay. I think this is all the basic physics, so I didn't prepare for that, but still I'll just try to mimic those pictures. I think the boron is a trivalent, okay, and it doesn't create one of the bond, but it does create a bond, covalent bond with the other silicon atoms. So in this case, when you try to break this particular bond or try to remove a hole that already exists, because in this case there exists a kind of hole because it doesn't create a kind of complete bond over here. Okay, so when you try to remove one of the hole, it leaves out a kind of electron. Okay, and this electron is additional to my boron. Okay, so for boron I need only 3 valence electron, but just because of the removal of hole, because of the depletion region, this boron has got an extra electron, and due to which it becomes a kind of negative ion. Okay, did I answer your question?
Oh, yes, sir. Yes, sir.
Yeah. So just because we have removed a hole, it just creates a kind of electron which is more than what is required for the boron, and due to which it becomes a negative ion. Okay. Yeah. So now these ions are generally immobile. Okay, they are not free carriers. And whenever I say that they are not free carriers, it means that you cannot use them for conduction of current. Okay. And again, the word depletion also conveys that you don't have any free charges here in order to make the current to flow through them. Okay. So generally, this depletion layer can also be considered as something like a kind of dielectric medium. Because in the case of a dielectric medium, it has a property that it doesn't have any free carriers. Okay, the same property that I had for a dielectric medium has also gone into this depletion region as well. The same type of definition. Okay, even the depletion layer doesn't have any free carriers, which means that they can also be thought of a kind of dielectric medium. Clear? And we call this particular mode of operation, when I have the potential of V, which is between 0 to Vt, we call this mode of operation as depletion. Okay, the next comes, obviously you would have guessed, what happens if I try to increase the value of V beyond the value of Vt. So in this case, the value of V is greater than the value of Vt. Now, whenever I have a voltage that is more positive, what it really means is that I have tried to deposit more number of charge carriers on this particular interface between the metal and the oxide. When I say p-type, it also has a magnetic carriers. So the magnetic carriers of this p-type is nothing but the electrons, and these electrons would then get attracted towards the interface. Okay, and after this concentration of electron, you would have again those immobile charge carriers. Okay, so there will be depletion region surrounding them. Okay, and after this you will have the free carriers, which are all holes for the p-type semiconductor. Okay, and now what has happened is that you could see that there is a kind of change in the type of material, because we know that a p-type material should have free holes, but when I see here, you could see that the type of free carriers that I have in this particular zone is completely inverted, which means that I have changed this layer from a p-type material to an n-type material, because I have more number of electrons rather than more number of holes. Okay, so here the majority carriers has become electrons, and due to which the layer has changed from p-type to an n-type. Okay, and we call this particular action as inversion. Okay, so if you have any doubt in this regard, you can ask. Okay, so and in the meanwhile, I will also show you a better picture, because I know that my drawing skills are not that great. So I always use some sort of presentation to compensate my drawing. Here in this case, rather than V, it is taken as Vg. When the value of Vg is less than 0, which means that we are trying to apply some sort of negative potential across the metal. And you could see that there is a greater number of accumulation of charge carriers at the interface between the oxide and the semiconductor. But when I have a value of Vg that is between 0 and Vt, you have some sort of depletion. Okay, so there is no free carriers in this particular zone. And what I would have is a kind of immobile negatively charged ions would be placed here. Okay, and after then, when I have a voltage of Vg which is greater than the value of Vt, then I have some sort of inversion. Okay, I have a majority carriers filled completely with electrons, and then there is a depletion layer, and then I have this normal p-type semiconductor at the bottom. Okay, so we call the first action as the accumulation, and the second action as the depletion, and the third action as the inversion. So we basically have three modes of operation when I take a metal oxide and a semiconductor structure. Okay, so hope that it is clear. So let's move on to the next one, which is about different regions of operation. Okay, and then we'll revert back to the MOS structure when we discuss about the CD again. Now let me take an N-type. It's just going to be a revision. I'm not going to teach anything new here. Okay, now we know that whenever the value of VGS, okay, so let us assume that the source is at the ground, okay, and I have some sort of potential difference between the source and the gate, which is marked as VGS here. Okay, and similarly, let us have some sort of voltage between the drain and the source as VDS. Okay, so under different conditions, let us see whether there exists a current or not, and we will also try to write the value of the current expression here. And in the next class, I will try to show you the derivation of it, okay? Because derivation is more important, but I thought the derivation would be much more relevant when we talk about second order effects, okay? So during that time, I will again revisit the same equation, but I will show you with the derivation, okay? So now let us have a value of VGS that is less than VT, okay? So now during this particular time, what happens across this particular oxide and the semiconductor? We just now have seen, right? So whenever we have this kind of condition, the MOS structure will be in
Depletion.
Yeah, it will be in the depletion. Yeah, it will be in the depletion region. So I will not have any free carriers here, but rather some sort of depleted regions would be there. And even across this PN junction, there will be a depletion region. Okay, it will be something like this. There doesn't exist any channel. Okay, now whatever the value of VDS that I have right now, will it have any kind of current flow between the source and the drain? Now, when I have this as my condition, you don't have any channel at all. Okay, there is no possibility of any charge carrier to move from source to drain. And I'm okay. So probably I have to put a word. It's a long channel device is what I'm talking. Okay, so let us assume that the length of the channel L is around 5 micrometer. Okay, so in this dimension, you will not have any type of current flow between the source and the drain. Okay, so because there doesn't exist no channel, any value of VDS will not give us any kind of current. Okay, so due to which the IDS will always be equal to 0, and we call this as a cutoff region. Okay. And now let us go for the next condition, where we have the value of VGS that is greater than VT. And I also assume that the value of VDS is equal to 0. Okay, so let me have the same potential as that of my drain. Okay, now in that case, what happens to our structure? So as you know that I will have more number of positive charges here. Okay, and in turn, since because the value of VGS is greater than the value of VT, in turn it attracts the minority carriers from the p-type as well as a little bit from the N plus regions. Okay, so we will not worry about from where these electrons has come from. Okay, but in short, I would have some sort of electrons getting attracted towards the oxide and this semiconductor interface, and below that I will still have the depletion region, and below the depletion region I will have the holes. Okay, so throughout this entire region I will have the holds. Clear? So here right now I have actually created some sort of bridge between the source and the drain. Okay. Now under this condition, what would be the value of this IDS? Any guess? Okay, so let me have two options for you. Okay, one option is equal to 0. The other option is not equal to 0. Okay, we will not talk about what is the expression for it, but rather I just want to emphasize only on which among these two options are true.
So A.
Okay, the option is A. Okay, how about other people? You can take
Sir,
anything.
A.
Okay, so 2
Sir,
A's.
A.
Sir, A.
Okay, 4.
A only.
Sir,
A, sir.
Okay, so majority of the people are opting for A. Yeah, the answer is A. The reason here is that even though we have created a channel, it is something like I have a resistance. Okay, the channel could be visualized as some sort of resistance. Okay, but this resistance, whenever the potential difference between the node A and node B are same, there won't be any current conduction. Okay, so the IDS or ID or the current through this resistance would be equal to 0. So the value of I that flows through the resistance can be written as VAB divided by the resistance value, right? Now, if at all, if I assume that the value of VA is exactly equal to VB, or in short, if you're familiar with phi A and phi B, okay, so you can use either of these two notations. Okay, so sometimes in your field theory you would have used phi term, I guess, which is nothing but the potential again. Okay, so if these two potentials are same, then we know that the value of or the expression for VAB can be written as VA minus VB or phi A minus phi B. Since because both these expressions are same, okay, or VA is equal to VB, they actually cancel each other and we would have no potential difference across them. Okay, and due to which the current will also become equal to 0. Clear? Now in this case, I have VDS value and the value of VDS is taken as 0, right? So which means that whatever the source potential that I have, if it is exactly equal to my drain, then we will have a VDS that is equal to 0, right? So under such condition, our current IDS would be equal to 0. Okay? It is just as simple as what we have discussed with respect to a resistor with a voltage of VA and VB across it. Okay. Yeah. So now let us depict the condition where when I have VDS that is greater than 0, I have still VGS that is greater than the value of VT, but right now the value of VDS is actually greater than 0, but still it is less than the value of VGS minus VT, okay, or VD sat. I think you are all familiar with this VD sat expression, right? Okay, so VDS sat for a long channel is written as VGS minus VT, or in your AMC you would have learned as DOV or overdrive voltage. Okay, so if the value of this VDS is less than the overdrive voltage, then will there exist a current? Again, I have IDS that is equal to 0 and IDS that is not equal to 0. Okay, let us see what type of answer that you have.
B's.
Yes.
B.
Okay.
B.
As you know that whenever there is a potential difference across the resistance, when the VA potential is different from the value of VB, then obviously the current would not be equal to 0. Okay, so due to which I would opt for the option B. And which region is this particular transistor right now is in? What do we call this region of operation?
Linear.
Yes, exactly.
Ohmic.
Linear or ohmic. And we know that the expression for IDS can be expressed as Kn dash W by L, VGS minus VT, and then VDS square by 2. Okay, and sometimes this Kn dash, which is a process parameter, is nothing but it's equal to mu n times that of COX. And now when we have a subject which is a VLSI, we normally will not deal with Kn dash or something like that. Okay, we have a parameter known as beta. Okay, and this beta is nothing but it's defined as mu n COX into W by L. Okay, so we'll be utilizing this beta factor rather than this Kn dash, which you would have normally used for AMC and AICD courses. Okay, so these are the notations that they generally use it, but for DVD, we will be using this beta, okay? And we generally call this W by L factor as something like aspect ratio, okay? And the whole of this derivation I will do in the next class, okay? So I'm just assuming that you're already familiar with this expression, at least the form of this particular expression. Might not be how you got it, but you might be remembering the expression of your linear current equation. So with that in mind, I just wrote on this expression right now, clear? And we say that our transistor is in the linear regime, okay? And now let us go for the final thing where the value of VGS is greater than VT and the value of VDS is greater than VDS sat, okay? Now, obviously, we have some sort of positive potential difference between the source and the drain, and due to which we have already seen that the current is no more equal to 0, but rather we have some sort of current that flows between the source and the drain, okay? Now, because we have this condition, what generally happens to our channel is what I just want to depict here, okay? And we already know that there exists a kind of depletion region around this particular zone, and because we have a value of VGS that is greater than VT, we also know that we have some sort of electrons filling this particular channel, okay? But right now, as I increase the value of VGS, which is greater than VDS sat, what is happening is that the potential difference between the gate and the drain also becomes smaller and smaller, okay? So due to which, what happens is that we will not have enough voltage difference between the gate and the drain in order to create some sort of channel, okay? So what it means is that when the value of VGD becomes less than the value of VT, the voltage difference between the gate and the drain, when it becomes less than VT, it is as similar to what happened when we had the cutoff, okay? So in this case, whenever the voltage of VGS is less than VT, we said that there exists no channel right from source to the drain end. But in this case, we have, when I compare the voltage difference between the gate and the source, obviously the voltage difference between the gate and the source is more than the value of VT. So we will have lot many charges here. But when I compare the voltage difference between the gate and the drain, we don't have the potential to create a channel, okay? The potential has been dropped below the value of VT, and due to which the channel will be something like a tapered region, okay? And we call this as a kind of pinch-off condition. And we say that the transistor has got into the saturation regime, okay? More specifically, when the value of VDS is equal to VDS sat, then we are at the pinch-off condition. But now, let us try to increase the value of VDS greater than the value of VDS sat. Now what happens? This channel will keep getting tapered, okay? So right now you could see that the channel is being shortened, okay? You have a lot of electrons in this particular regime, but you don't have any electrons in this particular zone. No electrons exist in this particular zone as you go beyond the value of VDS sat, okay? And again, when you try to increase the value of VDS further, okay? Now obviously what happens is that your channel will further getting tapered, okay? And you will have only electrons within this orange zone, okay? Within this orange zone, and it leaves out no free carriers in this particular regime, okay? So there won't be any kind of free carriers in this particular regime, okay? So this is what we call it as a channel length modulation. Anyhow, I'm restricting today with lot many things. I'm not going in mathematical terms as of now, okay? I will revisit the same concept again when we talk about the second order effects in the coming classes, okay? But as of now, you could see that the channel length is basically becoming shorter and shorter in this particular zone, okay? Now, as I said, right now, the value of VDS that I have is greater than the value of VDS sat, okay? So this means that this VDS can be split into two components, okay? One is the component of VDS sat. The other one is this delta VDS, which is the value of VDS that I have added extra in order to make this value of VDS much greater than the value of VDS sat, okay? Are you clear with these two expressions? I'm saying that currently I have a potential difference between the drain and the source, which is greater than the value of VDS, okay? So what does it mean? That I can visualize this current value of VDS as a summation of VDS sat plus the extra voltage that I'm applying, okay, as delta VDS. Okay. Now the question is, how do I visualize those potential drops across this particular channel area? Okay, let me just pick this particular condition, and I'll just remove this orange colored structure. And the channel has right now got pinched off, and the channel length also has got shortened. Okay, so this is our channel length, and there is a reduction in the charges. I don't have any channel charges in this particular zone, which we call it as delta L, and the region where I have complete charges, that particular length, we label it as L minus delta L. Hope that you are clear with these notations that I'm writing right now. Okay, the length where I have the channel, we have it as L minus delta L, and the length of the channel where I don't have any charge carriers but just the depleted ions, okay, we call that as delta L. Okay, now this is the condition that I have. Now I have a potential difference between the source and the drain, and I know that this potential difference can be visualized as two components. Okay, now how these two components can be visualized on across this particular channel between the source and the drain? Any answer for this?
Sir, can you repeat the question?
Yeah, so I'm having a voltage VDS which is greater than the value of VDS sat. Okay, now how much greater I can represent with something like VDS sat plus delta VDS. Okay, so the value of VDS can be returned as VDS sat plus delta VDS. Now I have two components for the expression of VDS. Now how are these two components are being mapped onto the channel? Where does these two components appear? Say for example, if I have some two resistances, okay, I have 5 volt here, and if I assume that both the resistance are same, then I know that this potential across this would be like 2.5. Okay, so in that way, you know that there is a drop of 2.5 volt and there is a drop of 2.5 volt. Okay, now in this case, this 5 volt can be mapped to VDS, and this 2.5 volt can be mapped to VDS sat, and the next 2.5 can be mapped onto delta VDS. Okay, so in that way, I just want you to visualize, like across the channel, how does these two components of the component number 1 and component number 2 appears, or across what element it appears?
Sir, delta L is for delta VDS.
Exactly. Okay.
Minus delta.
So the voltage of VDS, which I supposed to have between the source and the drain, is actually split into two components. The value of VDS sat will always appear across the channel where there exist charges. Okay, and the remaining part where I don't have any free carriers, this delta VDS would then appear. And when I look carefully, as I rise the value of VDS, okay, by a step, okay. So let us consider that I am just increasing by a proportion, and due to which I have a higher potential across my VDS2. Okay. Now what would happen is, like, I have to redraw it again. Okay, I'm talking about this condition where the value of VDS2 is higher than the value of VDS or delta VDS. Okay, now due to which the channel has been tapered very strongly than compared to the previous condition. Okay, so let me just try to get the condition, and there exist electrons in this particular zone. Okay, and right now the delta L is comparatively higher than compared to the previous delta L length. And this one has again got dropped. Okay. And this is my channel length. The total length of my channel is given by this L. Okay. So now, if I again see this VDS2, which is higher than the value of VDS, the value of VDS sat, whatever the voltage it is, it always falls only across the channel where I have the free carriers. Okay. And any increment that I have further increased beyond the value of this delta VDS, say for example delta VDS2, then this delta VDS2 would then fall across this delta L. Okay, maybe I have to write it as delta L2. Okay, so the relation between this delta L and this delta VDS is almost proportional. So what it means is that by whatever fraction by which I try to increase this VDS, even my delta L also proportionally it increases. Okay, if I higher this value of delta VDS, even the delta L also widens up. Okay, so this is the kind of relation that I could see when I try to bias the transistor in the saturation regime. Okay, and due to which one could actually rewrite this expression as something like. So since because they are actually proportional to each other, I've just introduced a kind of proportionality constant which is known as lambda prime. Okay, so the lambda prime is just the proportionality constant, okay, which has a unit of meter per volt. Yeah, okay. So we end up having this, and one can also talk about the channel length modulation effect here. I think today I thought I will talk about the CV error, but CV error within this next couple of minutes I cannot start and stop. So what I do is like I will just try to talk about the channel length modulation effect. Okay. Now channel length modulation is nothing but it's an effect where the length of the channel is being modulated by the value of VDS as shown here. As I raise the value of VDS, what is happening is the length of the channel where I have the charge carrier is getting modulated. Okay, and that's the reason why we call this as a channel length modulation. Now let us try to adopt this channel length modulation impact onto our current equation and see how does it going to affect my IV characteristics of a MOSFET. Okay, we know that the saturation current can be written as, and right now the current length of the channel is no more equal to L, but rather it is equal to L minus delta L, because this is where I have charges, and whatever the current equation that I have written here is just the drift current. So I have to look where exactly the drift is happening. Okay, the electric field that happens between this point and this point, okay, is where it makes me to move the carriers, and due to which I would write that the length of the channel is written as L minus delta L. Okay, and now one could pull out the value of L and end up having something like 1 minus delta L by L out of this equation. Now, I think you are familiar with this binomial series, which says that whenever you have some sort of expression, something like this, one could approximate this expression to be equal to 1 minus x, if provided if the value of x is much smaller than the value of 1. Okay, so under this condition one could approximate this expression to be something like this, okay, to be approximately equal to 1 minus x. Okay, so now in this case we know that the value of delta L divided by L, which is a ratio of delta L by L, is much smaller than the value of 1, and due to which I could rewrite the current equation of IDS to be Kn dash W by L, and then this can be written as delta L by L into VGS minus VT the whole square. Okay, and we already had said that this delta L is actually proportional to our delta VDS or the extra potential, but it is always written, rather than writing it as delta VDS, it is by convention I just use the notation of VDS. Okay, so I've just changed this notation of delta VDS as just VDS. Okay, so do not get confused with this VDS here. Okay, and this is what I have, and now let us plug in the place of delta L as lambda prime times that of VDS. Okay, and there is also one more term that I can introduce here, just because these two are constants. Okay, for a given technology, I'm going to introduce a proportionality constant, which is lambda, which is defined as lambda prime divided by L. Okay, so that this guy lambda will have a unit of volt inverse. Clear? So rewriting this equation in terms of lambda. Okay, so hope that you found the difference between the lambda prime as well as lambda. Okay, and we call this as a channel length modulation. Okay, so now having got this expression, let us try to compare this expression with respect to a current equation or a saturation current equation without channel length modulation. Okay, so
Sir,
yeah.
it should be delta VDS, right?
Yeah, it's supposed to be delta VDS, but this delta VDS is what I supposed to have, but they are being offsetted when we are trying to plot a current equation. Okay, I have this IDS with respect to VDS. Let us have some sort of current. So this particular potential that I have here for the current value of VGS that I've picked, okay, is known as VDS sat. And this current is actually plotted only after this potential, okay? It is not plotted right from the value of 0 to this particular point. So there is a kind of offset that is being introduced, because all of the current that I'm trying to plot with respect to VDS scale is not plotted right from the value of 0, but the saturation current is actually plotted after the value of VDS sat. Okay. During the computation, I have to consider it as delta VDS, but while I'm trying to plot, in that case, I'm trying to utilize my VDS because I just know that the value of VDS that I have to currently deal is not just delta VDS, because the delta VDS can be equal to 0, or it can be any value which is greater than the value of VDS sat. But when I have delta VDS that is equal to 0, still this quantity will help me to push my current at this particular point. Okay, that is my VDS would then be equal to VDS sat. Okay, when the delta VDS is equal to 0. So it helps me to put the current at this particular point rather than putting this particular current value at this particular value of 0. So it just pushes, it gives me some sort of offsetting. Are you clear?
Yes, sir.
While drawing the graph, it is just helping me to push the particular point rather than here to here. It just pushes. Okay. For that reason, we are trying to adopt VDS rather than delta VDS. Okay. Yeah. So I think I'm just going beyond the time. So this leads to, because we have a proportionality constant with respect to VDS, with respect to IDS, we will have some sort of slope value, okay? And we call this as a kind of channel length modulation. And in the case of small signal model, it is because of this slope, we end up having a drain to source resistance as R0 or RDS, okay? Yeah, so I guess I thought I'll be covering this ID versus VGS and ID versus VDS graphs, okay? But I think the time has already clocked more than 4 minutes. Okay, we call this particular graph. I think you're all familiar with ID versus VDS as well as ID versus VGS graphs, right? I hope you are familiar with these two graphs. Okay, so in this case, you would have, so till the value of VGS that is equal to VT, the current would be assumed to be equal to 0, and after then you would have some sort of quadratic relation. Okay, so and again, in this case, we are assuming some sort of VDS value that is greater than 0. Okay, so under these conditions, we will have some sort of current to flow through this particular device, and we call the IDS versus VGS as the input characteristic graph. Can you guess what do we call the? Sorry, it is not called as an input characteristic graph. We call that as a transfer characteristic graph. And any guess for IDS versus VDS graph? What do we call this graph as? And why are we calling this ID versus VGS graph as transfer characteristic graph and not as input transfer characteristic graph or input characteristic graph? In general, this VGS would act as an input, whereas the IDS would be an output current. Okay, so there is a transfer from the input to the output, and that relation we call it as just a transfer characteristic graph. Whereas in this case, the IDS, as I said, it's an output quantity, and the value of VDS is also an output quantity. So in this case, both these quantities that I'm plotting across the X and Y axis are output, and we call this as an output characteristic graph. Okay, so let me stop here, and we will revisit on Wednesday.